Hi everyone, it is chapter 4. We're on to telescopes, the exciting stuff in astronomy. And to understand telescopes and how they work, we need to understand everything about light, because telescopes collect all different types of light, not just the light we see, but also other types of energy that is light. So let's go and learn a little bit more about it. Light comes to us from the sun, and it comes to us in the forms of bundles, abstract bundles of radiant energy from the sun. Now that's a lot to take in. So let's start at the beginning. Let's start at where the energy evolves from, and it evolves from the sun and what's going on there. Remember that the sun is a giant sphere of gases. There is no iron core to the sun like there's an iron core to the earth. The sun is just a massive sphere of gases that is held together and cannot explode because the mass of the sun is so big that the gravitational field of the sun is so strong that it will not allow an explosion. Amazing. And inside this core of gases is hydrogen, which, considering that hydrogen is the lightest element we know of, to have it be the biggest mass of this sphere really says something about how much hydrogen is in the sun. That nuclear fusion that we were talking about inside this core of the sun at the hydrogen core is not nuclear fission. Nuclear fission is atomic nuclear power plants, and it is also atomic bombs. Now, nuclear fission is breaking apart molecules. Nuclear fusion is melding together atoms, specifically melding together their nuclei. And in the core of the sun, we are melding together nuclei of hydrogen to form mostly helium and many other elements. In fact, the sun does this and burns through 500 billion kilograms of hydrogen per second. That's amazing. And it has done this for 14.5 billion years. Let's talk a little bit about the elements that the sun produces, and then we'll talk about the energy that the sun produces. The elements produced by the nuclear fusion of the sun, remember, meld together two atoms' nuclei. You remember from high school science that an atom has a nucleus at the center, and the nucleus contains the electrons and the protons. Melding them together with nuclear fusion is so strong that it produces elements. This is not the same type of molecular bonding, which is far, far, far weaker. This is producing new nuclei and new elements. By doing that time after time after time, the sun takes its hydrogen core, fuses it together to make a helium atom. The helium atom is 2 electrons and 2 protons in the nucleus. You can also use this type of fusion to create other elements in the periodic chart. And you know from chemistry that these are the lighter elements involved in the periodic chart. The sun can produce all of the elements up to and including iron at Fe for iron. And what's incredible is that really the only thing you need for life are the elements that are associated with what the sun can produce. Now, it doesn't produce a lot of iron, but after 14.5 billion years, you've got a good accumulation on Earth. What's interesting is, in addition to that, the only other things that we might take supplementation for as humans involve things like zinc, maybe selenium, and iodine and salt. Very few other things would we ever take as a supplementation to our life. These heavier elements are actually not produced by the sun, and they are really, the theory is that they came from a giant supernova that ended up producing the sun more than 14.5 billion years ago. That supernova actually had the energy to produce these heavier elements by fusion. The sun does not have that energy, but the supernova, it is theorized, did. That is why Neil deGrasse Tyson, in our original video in the first week, was talking about the fact that you are the accumulation of atoms that came from the edge of the universe. Because these atoms in your body, for instance, atoms of copper in your body, atoms of, what else is in here? Lead in your body, atoms of silver in your body, and you do have silver in your body, they are all from on the edge of the universe because they are not from the sun at all. Let's go into the energy that's produced by the sun next. In producing those elements, in moving from one highly energetic nuclei and fusing it to another nuclei, you're actually releasing an enormous amount of energy, because this nuclei that's melded together of two is much more stable than the hydrogen that was on its own, which is why hydrogen is so explosive and helium is less explosive. If you've ever studied the Hindenburg explosion, which was a hydrogen balloon, went up like that, and helium balloons do not burn nearly as hot and do not trigger nearly as quickly as hydrogen. So the helium is relatively more stable, and in making that fusion, you are releasing an enormous amount of energy. That energy travels through the vacuum of space to reach Earth 8 minutes later. How much energy is that? That energy is, like you notice here, the equivalent of 4 trillion 100-watt bulbs hitting the Earth every second. Amazing. You're used to energy from oil and coal and solar and wind. You're not used to thinking about energy hitting the Earth from the sun. You're used to measuring energy in terms of BTUs and kilowatt hours. How do you measure these packets of energy from the sun? And we can. The form of the packet of energy from the sun is known as a photon. And Einstein literally described a photon as a packet of energy, a packet of light. It's not an atom, it's not an electron, it's not a proton. It has no mass. It has no space that it takes up. It's easier to describe a proton in terms of its behavior because it has no structure. And the behavior is wave-like. For instance, if you saw a soap bubble resting on your hand, you'd see the waves of color in the soap bubble. That is a wave-like behavior of light. But then it's also particle light-like, because packets of photons hit the sensor chip of the camera on your phone and all digital cameras. So this photon has behaviors that are like a wave and like a particle. but it is neither of those things in structure. Then how do we measure it? Well, we categorize photons by wavelength. We call them UV. We call them visible light. We call them infrared light, X-ray light, gamma rays. We categorize them by their wavelength. We'll get into that soon. And the unit of measure that we can use is 1 over a wavelength. So we can use that as a proportional unit of measure. But let's stick with the wavelength. And right now, I'm going to move you to a video that is the best representation that I have of the wave form and the wave behavior of a photon. I've looked at a lot of videos. This is the best representation I could find of the video. You only have to watch the first 1 minute of this video. The rest of it, you don't need to watch. And it's the best representation that I could find to show to you the wave-like behavior of a photon. So watch B, and then we'll talk on C again.